Okay, today I'm going to go through part 4 of this run through. I did parts 1, 2 and 3 a few days ago, and unfortunately I was too busy to complete the rest of the paper. So this is the Pearson Edexcel Linear Physics exam, and it's paper 2, which is also called Advanced Physics 2. So it's kind of similar to the International A-Level Unit 5 in terms of the Year 13 content, but it also has Year 12 topics in it in addition, because linear means all of the content is examined in Year 13. So I think for Advanced Physics 2, the main topics are waves, because obviously that goes well with astrophysics. When you do spectra, for example, and materials, okay? So if you'll find that parts 1, 2, and 3 are in the same playlist, and this exam, I think, is on Friday, on the 9th of June again in 2025. So it's coming up next week. So I thought I'd add this to the repertoire because most of my videos are for the modular paper, and I now have some students who are also taking the linear exam. So we went through question 11 before, and we went through question 12 before. So this is the question which I'm going to start with in today's run through. So this is very useful for people doing either modular or linear, because the content in the nuclear section is exactly the same. So here, question 13, it says a fusion research centre was opened in a place in the UK called Rotherham in 2021. The centre has a device which tests materials in extreme conditions. Yeah, and the materials that they're testing are found inside a fusion reactor. Okay, now of course fusion reactors are not commonly used in technologically, they're still under research. So you've got to describe the conditions inside a fusion reactor. And the key term is extreme conditions. So what are the conditions inside a fusion reactor? What would they be? Well, it'd be like the center of the sun, very high temperatures, much higher than 10 million Kelvin. Okay? So I think there are hundreds of millions. I don't think you need to remember. Now, of course, if it's very high temperatures, then it is likely to be high pressure as well. And it's the extreme conditions are also because we have highly ionized plasma. So everything is ionized. So you're going to have lots of charged particles, and they're contained inside very strong magnetic fields. Okay? And you're going to create a lot of neutrons in the process of nuclear fusion. So there's going to be a lot of bombardment of neutrons. And of course, they're going to they're going to affect the materials that are found inside the fusion reactor. Okay, so if they're being bombarded, these materials are bombarding the materials that the fusion reactor is made of. It could affect their nuclear behavior, their nuclear reactions. They could actually change the nucleus. Okay, and that could cause potentially some issues which they is not the main purpose of the nuclear reactor. You want to create energy, but in the process, because there's so many highly energized neutrons firing around, and they're not affected, they can't be contained by the strong magnetic field because they're not charged particles, so they're going to be able to go through the magnetic field without being deflected, and they would hit the materials the materials that they're testing, which are part of the structure of the fusion reactor. Okay, hope that makes sense. So this is a common question, it seems, and it's more common in the linear than the modular from what I can see. So neutron bombardment as a condition inside a nuclear reactor. The next part of the question says the graph below shows the binding energy per nucleon, which is here. And basically the binding energy per nucleon tells you the stability of the nucleus. The higher up you go, the greater the stability is. And if you go up, you're releasing energy. If you're creating something which is high up on this curve, you're creating something stable, therefore it releases energy. Okay, it releases mass energy. So it's to do with Einstein's equation of E equals mc squared. The mass defect is the m, and that can release energy. Okay, and that's why nuclear fusion, for example, can create a lot of energy per unit mass. Okay, so it varies with nucleon number, the binding energy per nucleon. So as you go to heavier nucleons or heavier nuclei, you can see the way there is a peak here, and that would be iron. Yes? So iron is the peak of the binding energy curve. All right, so that's information they've given you in preparation for the rest of the question. Explain why the fusion of nuclei can produce large amounts of energy. Yeah? Your answer should refer to information from the graph. In other words, they don't want you to just talk, they want you to use the data on the graph. For example, you could say, for example, if hydrogen fuses into helium, what do the numbers suggest? So first of all, fusion of nuclei is when smaller nuclei fuse to form larger nuclei. That will get you 1 mark. Let's just change across to green. The process which results in a mass deficit, yes, so this process of nuclear fusion, it results in a mass deficit, which I call delta M, as larger nuclei are more stable than smaller nuclei. They're more energy efficient, okay? The binding energy per nucleon increases in these cases, okay? So this will get you a 2nd mark. Now, so for example, binding energy per nucleon for hydrogen is about 1 mega electron volt. So we're now referring to information from the graph, which is what they're talking about. Yes? And the binding energy per nucleon for helium is much higher, about 7 mega electron volts. So by doing this, the increase per nucleon is around 6 mega electron volts. So in fusing hydrogen together. So this is the amount of energy released per nucleon when you can fuse hydrogen nuclei into helium nuclei. And I think that would get you the 3 marks. Okay? All right, so let's have a look at the next question. So here's the mark scheme before I forget. Okay? That's what we just went through. So you can take away, a look at it in your own time. Question 14 we went through in a previous part. That's the rest of it. Let's have a look at what we haven't done. We haven't done question 15, so let's go into it. So in a star you get nuclear fusion, and here they have a question 15, which the photograph was taken by the James Webb telescope. Yeah, the space telescope, the one that is a replacement of the Hubble telescope. So it comes from the cosmology space section in year 13, so it's very useful for international A-level as well. Again, the syllabuses are almost identical. I haven't found many differences at all. And it shows a group of galaxies that formed shortly after the Big Bang, which was about 13 billion years ago, 13 to 14 billion years ago. So this is a picture that must be very, very far away, yes, to be able to look back in time. So they want you to derive the equation t equals 1 over h naught, where t is the age of the universe. Okay? So we know that v equals h naught over d. This is from the formula sheet, and we know that naturally velocity is distance over time, so you could put distance over time instead of v in this equation, and then you'll get d over t equals h naught d, and you'll notice that the d's cancel. So therefore you got 1 over t equals h naught. I should do it in green really for answers as my normal color. So the age of the universe is 1 over the Hubble constant, and that's what they asked us to derive, and I think that will be sufficient, where t equals the age of the universe. Okay, so all we did was we equated these two equations, yeah, and came up with another term where 1 over t is h naught. Okay, or therefore age of the universe is 1 over h naught. This is a common question in the cosmology section. It then says, state one assumption made in your derivation. Well, it's not our derivation, but the derivation they've asked us for. And the assumption is that the rate of expansion of the universe has been constant throughout the 13 billion years. Otherwise, you couldn't do such a simple comparison or use of the two equations. They wouldn't necessarily equate. So this Hubble constant assumes that it hasn't changed throughout the 13 billion years. The rate of expansion is more or less the same. Okay? Now here they're talking about units. The parsec is a unit of astronomical distances, and a parsec is this much in meters. Okay? So you can look up a definition of a parsec later, but for the sake of brevity, we just continue with this video. Okay, how do they define what a parsec is? Okay, so it's a parallax second, something to do with the parallax method. The accepted range for the Hubble constant is between 60 to 80 velocity in kilometers per second divided by the distance in megaparsecs. So here's 1 parsec. So that's what they do to get a value of h naught, which according to the measurements that they get has an uncertainty, and they know the value is somewhere in between 60 and 80. So you could say is h naught is 70 plus or minus 10 of these units. So we've got to use these units to make it nice numbers. Okay? But remember, Hubble, the h value, Hubble's constant, is 1 over time. Yes? Because remember, h naught is equal to 1 over the age of the universe. Okay, so basically it's a time factor. Then it says deduce whether the observations by the James Webb telescope in above leads to a value of h naught within the accepted range. Okay, now the value given was 13 times 10 to the 9 years. That's 13 billion years. You can change that into seconds because they've told us what 1 year is in seconds. So we put that in seconds. So this is the value that it comes in seconds. And remember, h naught is 1 over the age of the universe. Okay, so h naught would be this. If we did it in seconds, it comes to this value. So that would be the value of h naught based on the James Webb telescope observation. Okay, now if you look at the minimum value of the Hubble constants in the range that they're given, 60 to 80, if you do the minimum first, to change it into per seconds, you've got to realize that the h naught is v equals h naught over d. So remember, v equals h naught d. Yes, so you can say that h naught is v over d. Yes, so we have to say the 60 v is 60,000 meters per second, yeah, because it tells you that it's kilometers per second. It tells you it's kilometers per second there. So we've got to change the top into meters per second from kilometers per second, which becomes 60,000. And the bottom is megaparsecs. Yes? So a parsec is this many meters. But over here, it's megaparsecs. So that's a billion of those. So we got to change that divided by 3.1 times 10 to the 16. And then we got to, actually that should be 3.1. I think that should be 3.1 times 10 to the 22. Yes, because we haven't put the mega in. Yes? So we've got to multiply it by 10 to the 16. 10 to the 6 at the bottom. Okay? So if we get it right, this is the answer that it would be. And I think I just forgot to write this 10 to the 6 in and 10 to the 6 here for the maximum value. So we would then get the range per second. So the maximum H0 in per second values would be 2.58 times 10 to the minus 18 seconds. And the minimum value would be 1.94 times 10 to the minus 18 seconds. So you can see that the value that we calculated above, let's do it in blue, this value is in between this range. So this is the range, 60 to 80 Hubble constant units, if we use kilometers per second, and megaparsecs would give us per second. So you could then say that the James Webb Telescope, the observations are within the accepted range. Hope that makes sense. Let me just go to the mark scheme and see. Yes, you see, I forgot to multiply or show the 10 to the 6 that you need to get it right. Okay? So I apologize for not writing it in originally. It's a good thing I spotted my omission. Okay, so that's the bit we just done. It's part A3. Okay? And I think you can follow their worked example as well. Now they may have done it a slightly different method, but you can try and do it. You can do it one way to work out the range from 60 to 80 kilometers per second per megaparsec into seconds, or you could try to convert the seconds into kilometers per second per megaparsec. I think it's easier the way I've done it. I find it less confusing personally. Okay, but you can try it both ways. It is a very common question, yeah, having to convert these units from kilometers per second per megaparsecs into just seconds or per seconds, I should say. Okay? So you can see the range that we got is from the mark scheme. Okay. All right, so the next question is part B. And part B of this question is about the Doppler shift. The light from one of the galaxies, doesn't matter what it's called, but here is the name, had a redshift of 14. Now, if it's plus, it will be redshift, and that's mainly for my student because this is what she's finding confusing. The wavelength of light detected at the telescope was this. Okay, so that's the wavelength detected. It may not be the correct wavelength because obviously it lies within the infrared section. Yes, so it's redshifted into the infrared range, okay, from whatever it was initially, okay, because it's redshifted by a factor of 14, which means it's become longer, okay. So positive redshift means the wavelength has increased. We got to calculate the wavelength of light originally emitted. So we want to find the original emission, which is lambda, the bottom of this fraction. So we know the equation that they give you is delta lambda. Now delta lambda means put the observed wavelength and take it away from the wavelength if it wasn't redshifted. So delta lambda is lambda observed minus lambda original, or lambda not shifted, okay, divided by lambda not shifted. Okay, so these two lambdas are what we want to work out. So when we know this is 14, you basically have this equation, and the only unknown is lambda, but you've got lambda at top and bottom of the fraction. So you will see that it's 14 lambda if we multiply it out. Yeah, so you can put this lambda over there, multiply both sides by lambda, and then you can see that the brackets will open up, and you've got another lambda on the other side, so it becomes 15 lambda will be equal to the redshifted wavelength. And therefore you can then divide that by 15, and of course dividing by 15 makes it a much shorter wavelength, which is the original, yeah, and it comes to 2.67 to 3 significant figures, which is 2.7 times 10 to the minus 7 meters to 2 significant figures. Okay, and then it says, so that's basically how you use the Doppler shift equation. It then says, explain why the light emitted arrives as infrared. Okay, well, we know that the wavelength has increased from the initial emission in the UV range. Let's have a look. So it's 2.7 times 10 to the minus 7. Now visible light, yeah, so visible is 400 to 700 nanometers. So 4 to 7 times 10 to the minus 7 meters is the visible range. Okay, so you can see it's shorter than the minimum visible wavelength. So therefore, this is ultraviolet. Okay? Okay? So that's what they want you to notice. So the wavelength has increased from the ultraviolet, so on one end of the visible light, to the other end, the infrared end. Okay? So from initial emission in the ultraviolet end of the spectrum to the detection in the infrared range. Okay? Now this is called a Doppler shift, but it's actually due to the expansion of space or the universe itself. Yes? Since emission. So since it was emitted, space is expanded, so the waves, as they're traveling, have become stretched. The wavelengths get stretched as the source of light recedes away from us. Yeah? And that's what we mean by Doppler shift. But it's basically because space has expanded in that time. Okay? So it's a bit like we do in GCSE. You can draw the waves getting stretched apart, and that's what we mean by a redshift. Okay? The next part of the question says, one of the infrared detectors on the telescope is made from a material with a work function given in electron volts. This is the symbol for work function. Deduce whether this detector can detect light from this source. Okay, so we know that the energy is of light is a photon, is HF, but since we know the wavelength, you can change that to HC over lambda, so you can work out the energy of the photons that is emitted based on the wavelength that we've got. So the wavelength that is detected, I should say, which is the infrared wavelength. And you can see when H is given to you in the data sheet, and C is also given to your data sheet, it gives you a value in joules of this. So whenever you use this equation always gives you answers in joules. We then have to convert joules into electron volts. And the way you do that is by is to divide by the charge of an electron, yes, which is 1.6 times 10 to the minus 19. So it gives you a value in electron volts of 0.31 electron volts, which is greater than the work function. And since it's greater than the work function, it should be able to detect the light. Okay? Because it's an infrared detector, and if the infrared photons didn't have enough energy, they would not be able to give off photoelectrons. So basically, these 0.31 electron volt photons can emit electrons, and that's what we're detecting. That's how we use the detector. Okay, so this is another 14 marks. We've gone through another 2 questions to do with fusion on Earth rather than in stars this time, and how we use data to analyze motion in the Hubble's constant, for example, and how it can be used to work out the age of the universe. I hope you found that run through useful. It doesn't matter whether you're doing modular or you're doing linear, the questions are the same for these 2 questions that I've done. They could turn up in either exam. Now, Unit 5 is tomorrow, so this will be useful to people who are revising for Unit 5 if they just want to take a look at another question before their exam. Okay, that's it for now. Don't forget to show your appreciation, like each video that you find useful, and share it with any friends who are doing linear or modular, and make sure you're subscribed. Okay, thanks for watching. Bye for now.